In the last lecture, we gave a definition of what a continuous function on a certain domain is. So we say a function is continuous at some point in its domain if for every sequence of points you have converging to that point in the domain, you can say the sequence of outputs converges to the number f of c, where c is the point in the domain you are approaching. This definition is really defining the notion of continuity at a given point, the point we typically call c. More often, especially in this lecture, we talk about continuity as a more general property. So to give that a precise definition, we say that a function is continuous on its domain, or perhaps a subset of its domain, if it would satisfy the definition of continuity for every point in the domain. It's important here to point out that our notion of domain doesn't have to be the most general domain for a function. Often we're going to be talking about just a subset. So particularly a function might be defined on all of the real numbers, but in this lecture we'll often be focusing on some kind of subset like a closed interval from a to b. What we're going to investigate in this lecture is what can we say about how a continuous function behaves over a given domain, and in particular, does it depend on the type of domain in question? So can I say something about a function over one subset of its domain that I can't say over a different subset? The first property we're going to look at is that of boundedness. So let me go ahead and define what it means to say a function is bounded. You can probably visualize the definition just from the word bounded, but what we mean is that if you consider some subset S of its domain, if you can say that the absolute value of f of x is less than or equal to some number b for all x in the subset S, then f is bounded on S. In other words, the set of outputs that f takes over the domain S is a bounded set. Here are some examples. One example function you should always have in mind, because it can be an illustrative example or counterexample to different properties, is just a constant function. So suppose I take the constant function f of x equals 1 for all x in the whole real number line, so just a flat line if you were to graph it. That's a bounded function, and its set of outputs as a set is just the number 1. Our second example is f of x equals arctan of x. Arctan is actually a really nice function that's often overlooked in a calculus class, but it's a function which is actually defined on the whole real number line, and it looks like just one branch of the tangent function kind of laying on its side. As you go to negative infinity, it heads down to the value negative pi over 2, and as you go to positive infinity, it heads up to positive pi over 2. So it's bounded, and its set of outputs is living between negative pi over 2 and pi over 2. So for the number capital B you could say capital B equals pi over 2. That would satisfy the definition of boundedness for the arctan function, or you could let B be 100. So your number choice B here doesn't have to be like the best bound. You could pick really any B that satisfies this definition. Similar example would be the sine function. This function is bounded by the number 1. It's also bounded by the number 25. All three of these functions are bounded on the whole real number line, which means that if you took any subset of the number line, they would also be bounded on that subset. But let's talk about a function whose behavior and the conclusion that we would make for boundedness depends on the underlying domain S. If you take the squaring function f of x equals x squared, and you just considered S to be the closed interval from -1 to 1, it would be bounded on that particular choice of S. Right? In fact, you could take the bound to be 1, or you could take the bound to be 5. If you looked, however, on the entire number line, then it wouldn't be a bounded function. So this is the kind of thing to keep in mind, is that some of these properties that we're going to describe for functions depend on your choice of domain S. Okay, let's investigate 3 properties that we might want to be able to describe about the set of outputs of a function over a set S, and let's see if any of those properties can be inherited from properties of the domain S. Here we're assuming that f is a normal continuous function. And the first question is, if S is open, is the set of outputs that f takes over S open? So think about that for a few seconds. Can you come up with either a counterexample where the set of outputs would not be an open set? And if you can, the answer to this question is no. If you can't, then you might want to think about whether or not you could prove this statement. If you played around with some examples, you may have come up with examples where S was open and the set of outputs f of s was also open, but hopefully you were able to come up with at least one counterexample where the statement is not true. So the answer is no. And again, you want to have that constant function as a go-to function to try. If you tried it here, this would tell you that the answer was no. Say your domain S is the open interval from 0 to 1, that's an open interval. But the set of outputs is just the single element set 1. That's a closed set because its complement is an open set. Just for good measure, here's another example. Take the whole real number line, that's an open set, and then consider the function f of x equals cosine. Its outputs form a closed interval from -1 to 1. Most importantly here is that -1 to 1 is not an open set. So R is open, but the values that f takes on R is not an open set. Now same question, but with S being a closed set. So if your domain is a closed set and your function is continuous, does the set of outputs form a closed set? Again, take a little time to try to come up with either a counterexample or an argument that this would be true. This one is also false, but counterexamples can be a little bit harder for the second question than for the first question. In particular, as you'll see as we go through some of the results later in this lecture, you would not be able to come up with a counterexample unless your domain S was unbounded. So if you looked at just functions over closed intervals, like the closed interval from 0 to 1, you would never be able to produce a counterexample to this statement. But consider the arctan function on the whole real number line. R is both open and closed, so this is a closed domain. But arctan approaches -pi/2 on the left and approaches +pi/2 on the right, but never actually gets there. So its set of outputs is the open interval from -pi/2 to pi/2, which is not a closed set. If you don't like using R as your domain S, consider this example. F of x equals 1 over x squared plus 1 on the closed interval from and including 0 to infinity. When x is 0, this is exactly the number 1, but then as x grows to infinity, this number gets smaller and smaller. It approaches 0, but it never actually gets there. So in this case, your domain is closed, but your set of outputs looks like kind of like a half open closed interval from but not including 0 through 1. Last question now with our notion of boundedness. If S is a bounded set, is the set of outputs f of s also a bounded set? So try to come up with some counterexamples and see what you can get. Once again, the answer is no. If S is bounded, it's possible to come up with a continuous function f which is not bounded. So here's 3 examples. Take the tangent function, so your typical tangent that kind of shoots down and shoots up, on one of its regions where it's defined, so say -pi/2 to pi/2, that's a bounded set, but this function's set of outputs are unbounded. Somewhat similar type of example, you could take f of x equals 1 over x on the bounded set 0 to 1. It shoots off to infinity on the left, so that would be an unbounded set of outputs over a bounded domain. And again, somewhat similar, you could take f of x equals natural log of x, just the very left part of it, so from 0 to 1, but not going all the way to 0 where natural log is not defined, it shoots down to -infinity. So again, this is not a bounded set of outputs. So for that second question, I said that your domain had to be unbounded in order for you to come up with a counterexample. For the third question, when the domain was bounded, you needed to have a domain which was not closed to come up with a counterexample. And the reason why both of those 2 questions needed you to pick the right kind of domain is because of this first theorem. So our first theorem is that if f is continuous on the closed bounded interval from a to b, then its set of outputs over that closed bounded interval is also a bounded set. So here, boundedness of this type of S implies boundedness of the function. The proof of this statement is really neat, and the key is Bolzano-Weierstrass. What we're going to use is contradiction. We are going to build a sequence of points inside of this domain, the closed interval from A to B, and then show that that sequence is going to generate a subsequence which converges because of Bolzano-Weierstrass, but then we'll prove that it can actually converge. Here's how we're going to build our sequence. If not, so we're doing a proof by contradiction here, if not, then since my set of outputs is an unbounded set, perhaps it shoots off to positive infinity or negative infinity or both, I can find a point in the closed bounded domain from A to B so that the size of f of x1 is greater than 1. If I couldn't do that, then my set of outputs would be bounded by the number 1. Right, so assuming that my set of outputs is not bounded allows me to make this choice of just any arbitrary point in the domain where the output has got a size greater than 1. Now I want to build a sequence, and I want my sequence of points ultimately to lead to outputs which shoot off to either plus or minus infinity or maybe bounce back and forth arbitrarily large and small. So the next choice I'm going to make is that there must be a second value x2 in the domain so that f of x2's size is greater than the size of the previous point plus 1. Again, I can do that because if I couldn't, the size of f of x1 plus 1 would be a bound on my set of outputs. So there must be a way to choose this point x2 if the set of outputs is truly unbounded. I get two nice things from this choice of x2. One is that my output size is growing, and two, implicit in here is the fact that x1 is not equal to x2. So I'm choosing disjoint points, right, because x1 can't satisfy this inequality. Now we can keep going in this way. Since our function is unbounded, I could now pick x3 so that the size of f of x3 is greater than the size of f of x2 plus 1, because if I couldn't do that, again, our function would be bounded. So what we have now is a sequence of different points. The way we choose them ensures that xn is not equal to xn plus 1 for any n, and their size is growing to infinity. The fact that I'm ensuring that it's not only bigger than the previous one, but bigger than the previous one plus 1 means that our sizes are just growing and growing. However, all of our points live in a closed bounded interval, the closed bounded interval from A to B. Since this is a bounded set, Bolzano-Weierstrass tells us that there must be a convergent subsequence. Here I'm using the language Cauchy because I'm going to end up using a kind of Cauchy condition here to establish contradiction, but really Bolzano-Weierstrass says that every bounded sequence has a convergent subsequence. So there must be some Cauchy subsequence of points which is converging to some value x. Now this is a sequence of points which is converging in the domain of f. F is a continuous function, so that means that the sequence of outputs also has to converge, or in other words, the sequence of outputs must be a Cauchy sequence as well. It has to be tending towards something. But could this sequence of outputs really be Cauchy? Look at how we designed our sequence. We designed it so that our outputs are growing and growing, and they are at least one whole unit apart in terms of size. So let me just think about what it would be like to compare adjacent terms in this sequence. I'm not even going to choose an epsilon or a capital N here. Let's just grab any 2 points which are next to each other in this sequence of outputs. If this sequence were Cauchy, then we should be able to know that if we go out far enough, these 2 outputs would both be beyond some threshold, at which point they would be really, really close together. But using the way that we constructed the sequence together with the reverse triangle inequality, I can say that the distance between these 2 outputs is greater than or equal to the distance between the size of the first and the size of the second. That's the reverse triangle inequality. By construction, I actually know this inside number is positive. That's just how we designed the sequence, so I could drop these outer absolute values. Moreover, this first term I know is greater than the second term plus 1. Now we get that the distance between any 2 adjacent terms in the sequence of outputs must be greater than 1. There's no way that you could now satisfy the definition of a Cauchy sequence. If this sequence is Cauchy, then we should be able to go out far enough in our sequence that the distance between adjacent terms could be forced as small as we like, but now we're saying it's always greater than 1. Choose epsilon less than 1 and you can't possibly satisfy the definition of a Cauchy sequence. So what we can really say is that we could not design this sequence. There's no way for us to choose a sequence that behaves like this because then Bolzano-Weierstrass breaks down. We have already defined what it means to say that a set of outputs is bounded over some domain S. If a set of outputs is bounded as a set, it must satisfy the supremum property. So that means it makes sense to define the sup of the set of outputs over some set and the inf of a set of outputs over some set if the set is bounded. So we will say the supremum of the function f over the domain S is the supremum of the set of outputs that f takes over S if it exists, so if f is bounded above as a set. And the infimum of f over the domain S is the infimum of the set of outputs, again provided that infimum exists. Again, it's important that you don't only think about the function, but you also think about the set S. So let's look at a couple examples. On the left, we have the exponential function f of x equals e to the x. On any domain, this function would have an infimum because it's bounded below on the entire number line. So since we never cross this x-axis, no matter how you choose your domain, this function is bounded below by 0, so it's always going to have an infimum. Whether or not it has a supremum, though, depends again on the set S, so sometimes it would and sometimes it wouldn't. If our domain S is the entire number line, then we can say that the infimum would be that number 0, because our function heads down towards the x-axis but never actually gets there. And since it never gets there, we can't really call that a minimum. Just like with sets in the past, if f actually attains the infimum, so if the number that is the infimum exists in the set of outputs, then you would call it a minimum. If it doesn't, then the function doesn't have a minimum. So f has an infimum of 0 over the entire number line, but it doesn't have a minimum. Because it shoots off to infinity, it doesn't have a supremum. It's not bounded above. Let me change my domain. Now suppose S is negative infinity to 0. Then it has an infimum of 0, which is again not the minimum. But now it has a supremum of 1. The y-intercept here is the number 1. So it has a supremum of 1, and that is actually also the maximum because it really does attain it at x equals 0, which is part of our domain. Let's look at example 2. On the right, this is the function f of x equals x. This function grows without bound to the right and the left. So if you considered S to be the entire number line, this function would have neither a supremum nor an infimum. But that's not really what I'm interested in. I'm interested in intervals here. If S were the open interval from 0 to 1, kind of like it's pictured, so this is 0 right here, and this is 1, then S forever gets closer and closer to 0, but never actually gets there. So we can say that 0 would be the infimum of the set of outputs, but there wouldn't be a minimum. And similarly, we get closer and closer to 1 from the left, but we never actually get there. So the supremum of the set of outputs would be 1, but you wouldn't call that a maximum. On the other hand, if S is the closed interval from 0 to 1, then we both attain the infimum and the supremum of that set. So now you can say the infimum of 0 is actually the minimum, and the supremum of 1 is actually the maximum. Our next theorem actually has a name. It's a well-known theorem from calculus, and this is the extreme value theorem, which says that if you're looking at a continuous function over a closed bounded domain, like the closed interval from a to b, then your continuous function obtains its supremum and attains its infimum. In other words, the supremum is actually an output of the function for some input in the domain, and likewise the infimum value is also an output of the function for some point d in the domain. Since the supremum and infimum values are actual outputs, they belong to the set f of ab, it's fair to say that the supremum should really be called a maximum, and the infimum should really be called a minimum. So this is the extreme value theorem from calculus, that if you're looking at a continuous function over a closed interval from a to b, it actually obtains its extrema values. So there is an actual maximum value of the function and an actual minimum value of the function. Later, when we talk about differentiability, this result will come into optimizing over, say, an interval like the closed interval from 0 to 1. If you remember doing that kind of exercise from calculus, what you typically do with a differentiable function is you find all of its critical points, but then you also have to test the endpoints. And the idea is whichever critical point or endpoint gives you the top value is the actual maximum of the function, and whichever value gives you the smallest value is the actual minimum of the function. So this is leading to a strategy in optimization which we actually use. Let's do the proof. It's very similar to the proof that the set of outputs over a bounded domain is bounded. Again, the key idea here is going to be that we construct a sequence which is bounded, and Bolzano-Weierstrass allows us to note that there's a convergent subsequence. So here we go. From the theorem we just did, we know the set of outputs forms a bounded set, which means we know that there is a supremum and there is an infimum by the supremum property. Now we use that characterization for a supremum. If I just take the supremum value m, sorry I didn't designate here that I'm calling that m, but let's call that supremum value m, and I take off 1, and I look at the closed bounded domain from m minus 1 through m, there has to be some point from our domain that lands inside of this interval, because if there weren't, m minus 1 would be a smaller upper bound for the set of outputs. So since m is the least upper bound, something has to land inside of this interval. We're going to build up a sequence using this idea. So there might be many choices of x1. Just take x1 to be any input from the domain whose output is greater than or equal to m minus 1 and less than or equal to m. It's actually possible that the output is m itself, and that's okay. Just call this point x1. We have the first point of a sequence which we can now build. We have a kind of criteria for how to choose our points. What we're going to do is make a sequence x sub little n, so that for each natural number n, the output f of xn lives in the closed bounded interval from the supremum minus the number 1 over n through m. The idea is that as n grows to infinity, this region here gets smaller and smaller. So what we're assuring is that our sequence of outputs is actually converging to the number m. That's the idea. It's important to remark here that these points don't have to be distinct. In fact, it could be a constant sequence. The second remark I want to make is that the sequence lives in the closed bounded interval from 0 to 1, so Bolzano-Weierstrass guarantees that we have a convergent subsequence in the domain. So by Bolzano-Weierstrass, this sequence has a convergent subsequence. This is happening in the domain, and let's call the limit of this sequence C. Since our domain is a closed set, C has to live inside of the set. Alternatively, you could say that since all the sequence terms are greater than or equal to A and less than or equal to B, the order limit theorem on sequences tells you that the limit has to be between A and B. F is a continuous function though, which means that when we plug this convergent subsequence into F, that has to converge, and it's going to converge to what we can now call f of C because we know that C is in the domain in question. So now the sequence of outputs converges to f of C. But by the way that we've designed this sequence, we also know that the sequence of outputs has to converge to the supremum value m, which means that f of C and m have to be the same number. So there has to be some input C from the domain where when you plug it into f, you get that maximum value m. A nearly identical proof would then tell you also that there has to be an input D from the domain where when you plug it into f, what you get is the infimum value. Our next result is another named famous theorem from calculus. This is the intermediate value theorem. We're not going to prove this theorem. It's one of the intuitively most clear theorems in calculus. So this theorem says that if you have a continuous function on the closed bounded domain from A to B, and f takes different values at the endpoint, so f of A is not equal to f of B, then for any value y sitting between f of A and f of B, either f of A is less than y is less than f of B, or f of A is greater than y is greater than f of B, depending on how f looks on the endpoints. then there exists a c from the domain so that f of c equals y. Here's the idea. We have some closed bounded interval from a to b, and let's suppose that f of a is less than f of b. So here's f of a, and here's f of b. Now if y is any point between them on the y-axis, say y is here, and my function f is continuous, then there is no way for me to get from f of a to f of b in a continuous fashion that doesn't cross y. Okay, so here's a continuous function, and as you can see, we actually crossed the value y 3 times in this example. So what this theorem doesn't tell you is how often f of c equals y, nor does it tell you how to compute c. That's not clear from the theorem. All it tells you is that there is some point c in the domain so that f of c equals y, where y is any value sitting between the endpoints. Real-world ways of explaining this theorem is like saying if you hike from elevation 0 to elevation 1,000, at some point your elevation was 800. Or if you are driving a car and you go from 40 miles an hour to 70 miles an hour, at some point you were traveling 65 miles an hour, right? So these continuous motions, hiking up a mountain, accelerating a car, they have to run through every elevation from the base of the mountain to the top of the mountain, or every speed from your starting speed to your ending speed. You can't skip over any output values with a continuous function. One of the mathematical uses of the intermediate value theorem is to try to find roots of a function. So consider this degree 5 function, which I can't factor, and it's also hard for me to just offhand sketch a picture of this, but I can try to figure out where the roots of this function might lie. And this problem prompt claims that you can find a root between x equals 0 and x equals 1. So let's verify that this problem is correct. What I can do is plug 0 into my function, and I get f of 0 equals 0 to the 5th plus 0 minus 1, whereas f of 1 is going to be 1 to the 5th plus 1 minus 1, which is 1. Therefore, so somewhere between the point 0, negative 1 and the point 1, 1, this continuous function has to cross the x-axis. I don't know from this picture where it crosses. Is it closer to 0 or is it closer to 1? That's not clear, but what you could do is now plug in the value x equals a half, so long as you can compute that. And if x equals a half is negative, then you can look for a root between 1/2 and 1. Whereas if x equals a half is positive, you could look for a root between 0 and a half. Our next definition is a new type of continuity that's a little bit different from the kind of continuity that we've been talking about, which is continuity at a point. This is a stronger form of continuity. So what we say is that a continuous function f is uniformly continuous on a domain S. That's really one phrase. So it's uniformly continuous on the domain S if for every positive number epsilon there is a positive number delta, so that for all x1, x2, sorry, that should be S, any pairing of x1 and x2 from S, if x1 and x2 are less than or equal to delta, then f of x1 minus f of x2 is less than or equal to epsilon. The idea here is that there's no anchor point C like there is in the definition of continuity at the point C. Rather, I'm saying f has got this property of uniform continuity on an entire domain S all at once if any arbitrary pairing of x1 and x2, which satisfies the property that their distance is less than or equal to some number delta, automatically tells you that f of x1 minus f of x2 is less than or equal to epsilon. Let me illustrate this definition with the function f of x equals x squared. The question is, if I want to ensure that any two outputs are within distance epsilon to each other, so let me imagine that distance epsilon between two outputs on the y-axis is like this. This region here, this height of this block I've just drawn, is epsilon units high. So any 2 points inside of that block are within epsilon of each other. Is there a way to come up with some positive number delta so that any 2 inputs from the x-axis being within delta distance of each other guarantees that their outputs are within epsilon of each other. Now I'm going to kind of scoot epsilon down like this. So say I want to compare those two inputs. These are pretty far apart, right? So if I take any two inputs from within that vertical zone, their outputs will be within epsilon of each other. However, if I raise epsilon up, then notice that the inputs I choose have to come from a much narrower zone because our function is getting increasingly steep. So now, any delta I choose based on this newest picture would have to be fairly small so that this width, this vertical width on the x-axis is fairly small. But then if I do this again, say I look at outputs higher on the y-axis, which are within distance epsilon of each other, now their inputs have to be really, really close together. So what we're illustrating is that you can't pick one delta which will work across the entire x-axis, because as you slide to the right, your delta is going to get increasingly small. It's going to get smaller and smaller. So this function is not uniformly continuous on the entire domain from 0 to infinity. However, we can prove that it's uniformly continuous on 0 to 1. What will work on the domain from 0 to 1 is illustrated by this picture that if delta works on the right half of the domain, say very close to 1, then it will work as we travel left. So it's like I want to think of the right side of this domain as the worst case scenario. In particular, if x1 and x2 are near 1, then the size of their sum is near 2, but it's certainly less than or equal to 2. Okay, so that's actually a fact that's true about all choices of x1 and x2 in the domain. So let me go ahead and point that out. So for any choice of x1 and x2 in our domain, the size of their sum you can break apart using the triangle inequality and say that's less than or equal to the size of the first one plus the size of the second one. But since we're in a bounded domain this time, those numbers aren't going to get arbitrarily large. In fact, that sum is less than or equal to 2. Now I'm going to prove that this function satisfies the definition of uniform continuity. So let epsilon be any arbitrary positive number. And what I'm going to do is pick delta to be greater than 0 but less than or equal to epsilon over 2. Then if x1 and x2 are any arbitrary inputs from the domain, satisfying that the absolute value of x1 minus x2 is less than or equal to delta, what we find is that the distance between their outputs can be simplified using difference of squares. So the distance between their outputs is the absolute value of x1 minus x2 times the absolute value of x1 plus x2. The first term is less than or equal to delta because of how we chose x1 and x2. So this term is good. And even if we were looking on the domain from 0 all the way to infinity, this first term would still exist and it would be less than or equal to delta. However, from 0 to infinity, the second term grows without bound. That's why we can't make this proof work on the entire larger domain. However, between 0 and 1, that second term is less than or equal to 2. So now we have that if x1 and x2 are any two arbitrary points in our domain from 0 to 1, the distance between their outputs is less than or equal to epsilon. So this function is not uniformly continuous from 0 to infinity, but it is uniformly continuous from 0 to 1. Therefore, this notion of uniform continuity depends not only on the function in question, understanding what the function itself looks like, but the underlying domain. So this is a statement about a function together with the domain. This example also illustrates another result we can make about how continuous functions behave on closed bounded intervals. This is another statement we're not going to prove. Let me just illustrate it. Here's a continuous function on R. And the way I've sketched this function is not uniformly continuous on R because it's getting increasingly steep as you travel away. However, if you restrict your attention to any closed bounded interval from A to B, this function will be uniformly continuous on that domain. Inside of this bounded domain, you kind of think about the steepest that your function could be. If you can pick a delta that works for your choice of epsilon in that very steep region, then it will work everywhere else. And this is something that we can do when we're looking at a closed bounded domain like this closed interval from A to B.